Okay, welcome guys. We are live in the second question. For A2, from 2010. So we're seeing a question that says define recursion. And second one says the following definition of function sub uses recursion. Dry run the call of sub AB with values A equals 5 and B equals 2 using either version A or version B. All the variables contain integer values. So they want us to choose from version A, which is in a different language. The plan is to dry run, which is basically line by line as this code progresses. What's happening? Show us what's happening. So you want to be able to tell them, okay, the first one is a function. It takes two parameters, then it executes an if statement. If the if statement is true, most of the next one. We'll see all that in due time. Then the third one is which line in the function is not tested in this dry run. Give it reasons different values for A and B which could cause this line to be tested. Do not carry out another dry run. It's actually 5 marks, so it doesn't make any sense to do the same thing you've done here to do here, right? So that's the question. Let's go into definitions and explanations and see how this fares. So catch you in the solution section. Okay, so let's define recursion, right? Recursion is simple in the sense that, well, it's not so simple, it's tricky. It's a tricky concept, but in programming, it's solved a lot of problems because it's kind of weird. We assume something has the ability to call itself. We give something the power to call itself again and again and again until, well, it has found a condition to be different from, when it starts. It's like creating your own while loops or for loops, but the concept here is that it is basically calling itself, and you have to include something in it that will help it change that condition. So let's give an example. For instance, so let's say you're a human being, right? As a human being, we had some ability to take functions and use them and then return them, right? So as a human being, with modularized set of functions, which could be things like sleeping, right? Walking, eating, drinking, running, because we actually see ourselves perform these things over and over again. And that's the whole concept of recursion here. We calling things and we're having a condition in place to help us break out of that thing when we are done with it, rather than just to keep calling it forever and ever again. So for sleeping, there are a few things that can wake you up, different things that can change the condition. So let's assume all you could do when you take up sleeping is to sleep. But then there's something that has to break you out of that sleeping condition, which are things like alarms and disturbance. For when you walk, you take one step after another, you are doing something recursively, you're doing it over and over again. And then when do you stop? Maybe when you have gotten to where you want to go. So gotten to destination, that's a condition that will help you stop walking, or you're tired, or maybe you see a friend on the road. Then let's talk about eating. Same thing, you take a spoon after another. You can stop when your stomach is full, or you can stop if the food is not interesting, or just tired also. So all these things are conditions that help us stop what we are doing to be able to break out of that and do other things, right? So drinking, same thing, maybe you're high already and you don't want to disgrace yourself, say you don't vomit and things like that. Then running is basically walking at a faster pace, so it's probably the same thing here, just that now the pace is faster. And when you've gotten to your destination also, you're tired, or you see a friend, or you trip and fall, or all sorts of things. Now the conditions for stopping a run is probably more than the one for stopping a walk. But this just implies that conditioning is necessary in cases of repetitive operations. A condition is necessary for termination. When we want to terminate, we need to put a condition in place, and that's the same thing recursion preaches. You need to always remember to put a condition to terminate the recursion, because it's a function calling itself. It's something that keeps calling itself over and over again. So they have running, you have all sorts of things. Now let's assume that there was a new function that human beings can perform, so that we can break this down and really understand what's going on. Let's say there's a function called laundry, and this function, the condition to stop it will probably be when your clothes are clean. So let's say you decide to wash like 200 clothes or 20 clothes. When all clothes have been washed, that is the condition to end this. So let's see what the function like this will be first and foremost, because a function, like we know, is a black box, right? You pass something into it and you get something in return. In here, a set of steps perform operation on the data that comes in and gives us an output. So this is what a function is in the simplest sense of it. Packing things together into one module and saying, okay, you take this, you do things with this thing, and then you give us that, all sorts of things. So that's that for that. So now, let's define what we do. Let's assume it's a function called laundry, takes your clothes. And the first thing it does is, when you want to laundry, what do? You pick a cloth and then you probably put it in water, followed by something like adding soap. Let's assume this is your style of washing. Some people put soap before water. Anyway, this thing mix in the end. Then you wash, right? And then you later rinse, and then you dry. This is a function. Like let's make it look like a function from C++. Yeah. Now this function has this step. So when you give yourself clothes to wash, you first pick a cloth, you put it in water, you add soap, you wash, you rinse, you dry. Then what do you do again? You pick another cloth. So you perform these operations over and over and over again. So what you can do now to make this a recursive operation, let's look at it, is to include a condition for which this thing will break. So what we can do is say, laundry clothes. You pass in all the clothes you want. You do this for the first cloth, right? Then what do you do next? You probably want to call it again. But this time, you want to call it with what? Less than one cloth. So you're going to say cloths again, but now you have removed one. So what happens is, let's say you give yourself 200 clothes to wash. First, you pick a cloth, you put it in water, you add soap, you wash, you rinse, you dry. Then you pick another cloth. So rather than picking another cloth and starting afresh and looping this one again, you can call the laundry option that you have, the function, to what? Give it another set of clothes. Now you're giving it 199 clothes instead of 200. 199 clothes, what happened? To pick a cloth, put in water out of the 199, to add the soap, to wash it, to rinse. So let's do a recursive tree to see what's actually going on. So laundry, you're giving it 200 clothes, right? Here, what does it do? You have the first option, pick a cloth. You have the second one, put it in water. You have the third one, add soap, wash, rinse, dry. Then, what else? Laundry. Give it what? 199 cloths. What happens for this? This one does the same operation, picks, puts in water, adds soap, wash, rinses, dries. And then what again? Does the same operation for what? 198 cloths. So we see these things going over and over again like this until it gets to the last place where it should have done all of this. Then we'll be doing our laundering for what? For the last cloth. Now, if you do not put a condition in place to ensure that this operation stops, now that we've gotten to the last cloth, then it's almost like a course where you now have to go and look for somebody's clothes. You can knock on your neighbor's door. Hello, do you have clothes for me? Because I need to wash clothes. You need to be able to stop this. So rather than have this thing loop continuously forever and ever, what we can do is to put some conditions in place. And how do you put conditions in place in programming? You use your if statements. So for the first one, I'll say, to ensure that this code continues to run over and over again for all the clothes I have till it gets to the last cloth, I'll put an if statement in place. And this is an indicator for the condition where if cloth is greater than or equal to 1, then perform these things over and over again, each time, reducing clothes by 1, then doing it again each time, then call the function again, which you pick another cloth, wash, call the function again, but now every time you are giving yourself lesser clothes from the 200 clothes that you have. Then I end this. That's if it is like this, do this. Else, right, if it is not, this condition is not met, then now we can terminate the loop that we are doing. So we can just put a return statement here, which will break out of the function, right? So it keeps doing this over and over again until it gets to the last cloth, right, where it will be 1. Then to get to what? Last one, what will be what? It will not try to actually come in again with 0 this time. So it will be laundry with 0. And what happens? A condition is not valid, and so therefore it moves to this block of code which says return. And this return statement is going to help us break out of this whole function completely, right? Because control has gone back to the main function here. So now all the clothes have been washed, dried, laundried, and we are now back out of the loop. And we can go and do other things like watch a movie, because you've done a lot of work for today. And so you keep watching the movie until when? Until the condition is met that you've enjoyed yourself. Or maybe somebody calls you, but you really deserve either therapy or this kind of enjoyment to have had to wash 200 clothes. 200 clothes, I don't know what you were doing, but yeah. So the idea is simple. Recursion is when a function calls itself over and over again, and it has to have a condition for which it can break out of that call. Otherwise, it will keep doing this thing forever and ever and ever. Something like a course. So I think we're done with that. That's recursion. The simplest time is just a straight line, but I just need to explain this to you because we'll be seeing recursion in the future. In the next question, we'll see recursion. So for now, let's just get back to the question set and move on to the next solution. See you there and then. Okay, so we have the next question. The following definition of function sub uses recursion. Do I run the call of sub AB with values A equals 5 and B equals 2 using either version A or version B? All the variables contain integer values. So we have two functions here. we're passing A and B into a function called sub, and A is going to be 5 and B is going to be 2. And we want to see what actually happens behind the scene. Now that's what dry running is. You're going to go through each line. It's like running the code like the machine itself, like the computer would, but you are the one actually walking through each line of the code. So you can see that there are lines on one side, 1, 2, 3, 4, 5, 6, 7, 8, and then the instructions on that match those lines in sub, if return, else, if else return. So your job is to walk through this code by going through with the lines that each instruction performs. So we'll see that in a second. So the whole point is, this is a function sub. You're passing it 5 and 2, A and B, 5 and 2, as it's stated here. Now this sub goes in here. This place becomes 5, this becomes 2. I won't be using this one because this is not what I'm familiar with. Let's jump into the explanation. So a dry run, right, as the name implies. So it's basically you running code with pen and paper like the computer would. And what does this entail? It means you're going to be going through the code line by line, telling us what line the computer will go into, and telling us what will happen, what variables are changing. So you're actually looking at memory. It's like looking at memory and telling us, okay, at this point in time, this variable will change. At that point in time, this variable changes, blah, 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 blah. That's the whole point of dry running. So dry running in a case of sub, first I'd like us to do a recursion tree so we can see what's going on. Okay, pardon my slight inclusion. I needed to because these lines are quite important to note. And when you're dry running, the simplest and fastest way, the best way I think, is to just imagine how the program works. So let's draw a function tree, a recursion tree, to see what's actually going on. The first line is in sub, right? Sub calling AB. So say sub calling AB. In this case, we'll swap this out. That's why we have something digital. Then it checks the condition. If B is greater than 0, it calls another function. Either it calls what? Sub A minus 1, B minus 1, or returns what? A, or it does what? It calls sub A plus 1, comma B plus 1. Now, under what conditions? This one will be B greater than 0. This one will be B equals 0. And this will be the last of these options, which is probably B less than 0. It's probably a negative number. So we have these three things. If the condition is this, do this. If the condition is this, do this. Then if it's this, perform this. So now let's look at sub 5 for sub AB, putting 5 in the position of A and putting 2 in position of B. So they said 5 here, we're giving 5 to be here and 2 here. So this could be redrawn as what? Sub 5, 2. Right? What happens? Which does it choose of the 3? It doesn't choose this one, doesn't choose this one, it chooses this one. So because B is greater than 0, right, it will be sub 5 minus 1, that's 4, 1. Then this one is a function, right? Remember, it starts to perform stuff. So swap this out from 5 to and put what? Put 4, 1. What happens now? What does it call? Does it call this or this? Is B greater than 0? Yeah, B is greater than 0 because 1 is greater than 0. So it chooses this again. And so it calls sub A minus 1. That's 3, 0. 3, 0 is the next big thing on the block. Which does it choose of these 3 pathways it can go? B greater than 0, it can't choose that because, well, in this case, B is 0. B equals 0, so therefore it returns A. So it chooses the path to return A. Now that it has gotten to the end of this, right, where it is returning, it starts to come back, starts to return control back to the ones that called the function that houses the return. It starts to return back to the previous return because remember, this one is to return this one is to return this one is to return this, and then this one is supposed to give us the final return. Then we'll get the final answer here. So 5, 2, 4, 1, 3, 0, return A. This is what is going to happen. So the computer is going to now let's draw a table based on what we've seen here. Right here, B is still greater than 0, so you want to put in all these things in place. Here, B equals 0. So with this diagram I've drawn, it's quite easy for me now to draw my table, my dry run table that will show me what's happening with all these variable changes. This tree is good. Now you know what will happen. And if you look at what this is basically a subtraction recursive function. You can see clearly subtraction 5, 2, 5 minus 2, 3 gives us 3. Okay, so let's draw a table. So I have a line for the line itself, right, to denote the lines themselves. Then I want to underline for what? Just look at your tree and start looking at the things you want to get out of it. I want to underline for the instructions. Instruction is to enter this place or enter that place. So that's the instruction. Then I want another line to store all these variables. So 5, 2. We're going like this. So I want variables. So I'll say for variable A, variable B. What else? Then you want to have a note, like a final note, an output, or a note, whatever it is you want to say at this point. But it's usually outputs or comment or something. But yeah, this is where she's showing us what is going to happen from that transaction that's happened in this code. So first and foremost, the code starts with line 1, right? Where it calls an instruction. Now this instruction is a function, right? And then what variable does this function take? It takes 5 as A and 2 as B. What does it do? Does it do anything? No, it doesn't do anything at this point. Then it moves into the next. After here, it checks this if statement, right? So second thing is to check what the if statement. We look at it on line 2 also. So yeah, it checks the if statement. So then I forgot to add something, right? If it's equating to something too, right? If it's going to either be true or false. So I want to be able to catch that here too. So I could put, let me just clear this out. So for the if statement, I'll put the output here. If it's true, right, B greater than 0, which is basically what it is here. B is greater than 0. If it's true, call the function again. So sub call, right? Call the function again, and this time it goes back to calling this function again. This function now. And that function is going to be what? Starting again. Function. Variable this time will be 4, 1. Then it moves to what? The if statement, which is on line 2. If what and what? This is greater than 0, which is true. And then the output is what? Still greater than 0. Then what does it do again? It tries to move on to the third line. This third line here. What is this? Another sub call. Then it goes back to calling the function sub again. So function, because it's creating a new function. Yeah. Function 3, 0. And then in this case, is it true or false? It's false, because B is now less than 0. So what does it do if it's false? If it's false, it skips this line 3, goes to the else. So it calls the else, which is on line 4. And then else, which is true now, right? It does another what? If statement, which is 5. It does another if statement, because B equals 0. So 5, if, right, if true, right, that's on line 5. What does it do? Return A. So what does this one return? It's true that B equals 0. So on that same line, it's supposed to return A. So the output here will be, since B equals 0, return A. Now, there's really no convention for doing dry run, right? The idea is for you to be able to show what's happening behind the scenes. So the whole line thing is to help us traverse. So using this structure, first and foremost, helps me understand what's going on. First, I have my function call. Then that function is passed what? Two things, 5 and 2. Then I check my if condition. If it is true, the if statement is true for B greater than 0, I'm going to call sub again, passing the function for 1. Then if it is true that B is greater than 0, which is true, then I'm going to call the function again for 3, 0. So it does this, if this, return A. And once it's done, it now ends the whole thing. Yeah, so that's that for that. I think we are good on track. Just draw a tree to help you understand what's going on if things are getting complex. Then, when you're done with the tree, you can now start breaking it down into pieces like this, where we walk through it, check the lines according to the lines here, and helps you break it down exactly what's happening. Some people might remove this sub call, right, because it's confusing, but put it in place, because every time you call that, then you want to differentiate that, okay, that sub call calls a function, then another sub call calls another function. So don't forget to put your sub calls before functions. That's that. So we're done with this. We can move on to the next level. See you. This follows nicely from the last question that says we should dry run. Now I said not dry run here, so we're just to check out what's going on. It said, which line in the function code is not tested in this dry run? Give with reasons different values for A and B, which would cause this line to be tested. So different values for A and B that will cause this line to be tested. It's quite obvious. I think I said it before at one point that this condition here talks about positive numbers. This condition talks about 0 itself. So this condition is less than 0. This is what will let us enter this third function, because that's what they're asking us. Which line in the function code is not tested in this dry run? So apparently we realized that when we started the code, first we went in the direction of this line first. We went with, how did we go? We went with this line first. Then we went with this line again. So we went to this line first. This line again, that is this. Then we went with again this line. right? Which is this. Then we went with this line. So apparently, actually, obviously, we only went with this section of the code. That's what we tested. This was our values went through. We never tested this section of our sub. So therefore, the part of the code that wasn't tested is this part. And this part can only be accessed if this condition is upheld. So this condition here says b is less than 0, and for b to be less than 0, that means the second value that comes into our sub function must be negative. So therefore, to test this, so I just say, okay, for a and b, for it to enter here, you're saying b has to be negative, right? A can be positive. Nobody cares about A. But B has to be negative for us to be able to enter here. So I can give you all sorts of values. I can say A is 5, B is -2, A is 4, B is -1. Just make sure that this section is -1. And that's the reason. The reason is because the code tests, partitions the recursion in directions of positive, zeros, and negative. But apparently what we tested with the 5 and 2 were only positive values, and they were greater than 0. So when it got to 0, yes, it terminated, but then we never got a chance to test the sub function that caters for conditions that are lesser than 0. So return just happens there and we're shut back out. Okay, so that's that. This is a simple subtraction function using recursion. You might want to put this down so in case you're told to write this up. So a function for subtraction using recursion. Design a calculator. You can just do something like this quickly. So let's check our answers, right? We've done this. We've done the dry running. We've done what we need to do. Now let's check our answers with respect to what the exam report says. So first and foremost, recursion as explained by them is a simple short sentence here. Functions are recursive if they call themselves. They must include a terminating clause. So all the things we've talked about so far, terminating clause, all the things we've talked about so far about functions calling themselves, about the conditions you need to put in place, blah, blah, blah. This is what it is. Just one line here, which is good enough. But you can go a little bit more into detail if you are scared or worried that this is too terse for the marks that you need to get. How many marks is it, by the way? That's 5 marks. Then we move on to the next table of dry running. Dry running here. Yeah, so you see what exactly almost like what we did. Yeah, so I have my lines as they happen, the function. When I do a sub call, I have a sub call again, and I go back in all the way. Then I think the difference is around here where I put my output and my notes together. They have to have the output and notes together. I put mine here, right? And I put true at the top of it, true here. But yeah, this gets the point across clearly. Now let's see what they said at the end of the day. Okay, then in line 3 said, line 7 was not called as B was always greater than A until it became 0. If we instead add A equals -5 and B equals -2, then line 7 will be repeatedly called until B becomes 0. So it means that the negative number for B is what will help us get into line 7 if we were running a test. But we weren't running a test for that because of what we gave it, which is why they asked us here to tell the reason why it never got to line 7. Okay, so exam guidance and notes. They said here some weird ideas about recursion, but majority have learned the definition. So most people just weird ideas. It's like, what are you saying, young man, about recursion? But majority have learned a definition. So it's a definition, everybody knows that. Then some weird ideas, which means some people try to go into extra reasoning about what they think recursion is and give us some concept of it. You could do that, but make sure your concepts are sensible so that won't be called weird. Generally done well despite some careless errors. That's the B part of it. Many answers spot by crossing out and altered figures. So what you want to do is emphasize clarity. You want to be sure that what you're writing down makes a lot of sense as far as clarity goes. So what you can do before that is to try to draw your tables on your question papers before you go and transfer them into your answer booklet. Candidates should learn how to carry out a dry run without either of these annoyances. So to them, it's actually quite annoying to have to go through a million people's questions and papers and see yours amongst the pile. Have this in a table format. That's quite crazy. Then C says done well if the dry run was okay. And so if you can answer this question, there's another 30 marks for you. So that's that. Thank you very much.